Hello and welcome back. My plan for some future videos will be to give you more concrete hands-on examples which illustrate how metric space notions and Hausdorff measures are encountered in the wild, basically. For today, the setting that we are in is a metric space. Remember, it's just a set and a distance function that satisfies the triangle inequality. Which in our case here satisfies two additional conditions. First of all, the topology that the distance imposes on X is homeomorphic to the standard Euclidean topology of R2. That means there's a continuous map from X to R2 which has a continuous inverse. The notion of homeomorphism is a more relaxed notion than metric types of isomorphism because there is no restriction on boundedness and things like that. You will see this in the examples. The second assumption is that this Hausdorff 2 measure is locally finite, which is exactly saying the second item here, that H2 of compact sets are finite in the metric space X. The theorem that we have says that if you have a closed and connected subset of your space which has finite Hausdorff 1 measure, informally we can say it has finite length, then you can write the set as a union of increasing sequence of compact and connected sets. So what have we achieved by doing so? We have moved from being just closed to being compact, and that's a big deal because compact and connected sets, which are also called continuum, if a set satisfies this too, it's called a continuum. We know a lot of things about these. They are basically curves. If you have been following my playlist on metric curves, we did talk about this, and there was some theorem saying when you can write a continuum as the image of a continuous map from the unit interval. So this theorem was something that we needed to do for a paper that I actually put on archive today, and it's going to appear on Monday. And just moving from that closed to compact was a big deal. So I'm not going to talk about this theorem and proof of it in this video. What I'm going to talk about instead is a counterexample when you remove this finiteness of length assumption. So a natural question always with any type of theorem is if the assumptions are really necessary. So in this case, is H1E finite necessary? Okay, and I will draw you a picture of a set that violates the conclusion of the theorem. But before that, let me also probably draw some pictures to illustrate what this theorem is showing us. First of all, if you are a closed and connected, well, it could be that E itself is compact. But in that case, we just can take all of these EIs to be E itself, and there is nothing left to be proved. So we're talking about closed sets that are not compact. If you are in the usual topology of R2 and this distance D is just the Euclidean distance, you cannot actually draw a set with finite length that is closed but not bounded, and connected but not bounded, because if you were bounded, you would be compact because you're also closed. That means your set has to leave to the infinity. But then because you're connected, you have to have a continuous set between them. And there are theorems that say that Hausdorff measure 1 will be bigger than or equal to the distance from this to that. So, and because now we know these points go to infinity, that will push h1 to be infinite. So you cannot do this with the usual distance on R2. If you are closed and connected with finite length, then you have to be compact. But we have an arbitrary metric space, and the only restriction that it is homeomorphic to R2. So what is another quite simple space which is homeomorphic to all of R2? So you can squeeze R2 with a homeomorphism inside a unit ball. So open unit ball, the interior of this set is homeomorphic indeed to B. You can actually write down explicit homeomorphisms, squeezing all of R2 into that. Remember, you only need continuous with continuous inverse. Now you can say that this is my space X, and the distance I put on this space is the usual Euclidean distance, as if this was sitting inside, again, a copy of R2. So you imagine this ball sitting inside R2 with the usual distance, and given X and Y, in the space X, their distance is just equal to the Euclidean distance of X and Y. Now, one has to check that the topology is the same. That's easy. What is interesting about this space X now is that diameter of X is in fact finite, unlike R2. You can also imagine that you have changed the distance. So X has a copy here under this homeomorphism, and Y is somewhere here. So you say that distance here, say d tilde of xy, is d of x and y. So let's put also tilde here to make sure what we mean. So if x and y are images of x tilde and y tilde, you can then define, you can set the new distance d tilde to be given this way. And in this case, again, in the d tilde distance, the diameter of all of R2 is finite, is actually equal to 2 and finite. So I'm assuming this is a ball of radius 1. Okay, so this is one way of thinking about the space X. You can imagine X is already just equal to R2, but there is a new distance, not necessarily equal to the Euclidean distance. Now we can give a non-trivial example of the type of set we are dealing with here. So you are in the space X. You are a closed set, but not compact. And here is one such example. This E is a closed set in a space X, because remember, X does not contain its boundaries. It doesn't see its boundaries. These are like the infinities of R2, which are not technically part of R2. So this is a closed set in X. If we go back to tilde world, this E is just an infinite line that goes to infinity on both ends. So it is closed. It is definitely connected. And it's H1 in the distance D is actually equal to just the length of E in the Euclidean sense, because the distance is just that. And remember, Hausdorff measure on set E, the distance is just the usual distance. Therefore, h1 measure of that is just h1 measure in the Euclidean distance, and there you go. So this is at most 2 and finite. So this is a kind of set that we're talking about in the assumptions of the theorem. So you have a closed connected set with finite h1. Then the theorem says that there will be an increasing sequence of compact and connected sets which exhaust it. So in this case, those EIs will be, for example, you can take from here to here, endpoints included, so you can take it to be E1. E2 can be from here to here, the longer set, and then you can keep increasing to exhaust all of E. So you see that the theorem, what theorem predicts here can be constructed by hand. So this is the type of thing that we are talking about. The set E itself may not be compact, but it can be exhausted by compact and still connected sets. Okay, now back to the question. What happens if we drop this assumption? Can you give us an example of a closed connected set which is not union of compact and connected sets? And that was an example that I found on my own and I just fell in love with. So the set that I construct is as follows. Let me draw the coordinate system in blue. So I will give you a subspace of the usual R2. Okay, so the distance is just the Euclidean distance. Now I need to give you the set E. I'm going to describe to you the set E. First, I put a function that blows up to infinity. This could be, for example, the graph of y equal 1 over x. And I'm only concerned about x positive. What I do then is, at some sequence of points that converge to 0, I include these vertical lines. So there are these bars hanging now and then from my graph. And I will have an infinite many of them. So this will be A1, A2, they increase to 0, A4, and so on. So limit of an is 0. And also to this set, I add the y-axis from 0 and above. Okay, so dot dot. These will meet at infinity. Both of these, of course, are pushing up to infinity. So my set E will be the union of graph of y equal 1 over x for x positive. Then the bars hanging at x equal ANs. And then there will be all the y-axis in the positive direction. So x is 0 and y is anything non-negative. Okay, so this set, let's see. So I will leave some of the details to you as simple exercises. So E is closed. If you have a sequence in E that converges somewhere, that somewhere belongs to E again. Or you can show that the complement of E is open. E is connected. That means you cannot find open sets U and V such that they separate E, such that E is contained in union of U and V. both contribute to covering E. That means E is not just in one of them, E is in both of them. And U and V themselves are separated, right? That's the definition of being connected. So it is closed and connected. Now comes the more important part, and that is, so remember so far I'm not committed even to any distance function on my metric space X. Let's actually erase this for now. We don't need to talk about distance for any of the following because they are all topological claims. So on this topological space, okay, so we borrow the topology of Euclidean space. E being closed and connected, all topological statements, they don't have anything to do with the distance function. And the lemma that I'm going to write also is very topological and has nothing to do with the distance function. E is not a union of an increasing sequence of compact, that means continuous, compact and connected sets. Okay, if we prove this lemma, then what follows is this. This will be a corollary of the theorem, which said that you can write some set as a union if, other than this assumption of closed and connected. So E is closed and connected if it had finite H1 measure. According to theorem, we could write it as a union of increasing sequence of compact and connected sets. But now that if we have this lemma, which says you will never be able to do so, it means that it will never have finite H1. So from theorem and lemma, we get this. Corollary. If D is any metric on R2 with topology so on these compatible with the topology, compatible with its standard topology. So we put a metric on R2 and we require that it doesn't change the collection of open sets. Topology. Then this set that I have drawn a picture of for you will have infinite measure, H1 measure. And this is so interesting because this is, to me personally, is the first time I see an example of a set that will have infinite measure no matter how you change the distance modular respecting the topology. Because topology and metric are quite different things, as you can see from this example of squeezing all of R2 into a ball. So topologically this is an obvious thing, but metrically there are restrictions. So it's not ever obvious that something about Hausdorff measures, which depend on the metric, will remain invariant no matter how you change the distance function. So this having infinite measure here is a consequence of the topology of E and is invariant under how you change the metric. In other words, some topological assumption restricts some metric quantity. And that I find really amazing. Now it remains to just prove this lemma. Why is E not a union of increasing sequence of compact connected sets? And let me explain that here. So suppose you have a compact subset of R2. What happens is that your set is bounded, right? Every compact set is bounded. So let me draw compact set. It doesn't have to be a circle, but it's easier to draw it this way. Because it's bounded and connected, so we want to find, so we're trying to say that you cannot write E as union of En, which are compact and connected. So because you need connectedness to be there, and because your set is bounded, you can pick at most, let me see, I did something stupid. Okay, so you can pick at most finitely many of these vertical lines, because after some time, the vertical line will actually leave this bounded set, and it will touch the graph only here in this region. Therefore, if you have, say, this one here and this one here, then the subset of En will not be connected, because there's no way you can connect this bar to this one within this compact set. It just, the connection happens here, which is outside your compact set. So if you're a compact set, if En is a subset of E that is compact and connected, then it picks at most finitely many of the vertical bars. Okay, so also for the same reason, if your subset En picks a point, say, from here or a point from here, then it cannot pick any point from there. Again, because you're bounded, you will stop somewhere before even approaching here. Well before approaching the zero, you will have to stop somewhere. And therefore, there will be this gap from this last time you pick a bar and this x-axis. And then your set cannot be connected, because the connection has to happen right here at infinity even. It's even more difficult to connect. So if your set En, if En is a subset of E that is compact and connected, and it picks some point here, then there are no choices for your set but to be of the following shape. It will be part of this graph, let's say this blue part, plus some of these bars. Like, I'm trying to be the most optimal. If En tries to be the biggest, because we try to cover as fast as we want, this is like the biggest it can be. And now if you go to the next one, this nestedness here is also restricting you. The next compact set you pick must again contain this blue, and again you will move a little bit to larger sets. You can add new things by increasing your bounded set. You can probably bring this in, but again you will have to stop at finite level. And therefore, union of En, or let's say none of En, such constructed, will ever pick anything from y-axis. So that union of such En, increasing sequence of En, will never be equal to E. They will always come short of covering the y-axis part. So you may wonder, what if we start with y-axis? Then what happens is this. So if you are in E1, say, without loss of generality, and E1 picks a point from here. The largest you can go, because you are connected, you have to pick all of y-axis. But then because you're bounded, there is a point you stop. You cannot go above this part. And then that would mean that there is no way you can also pick a point from here, because there is no way you can connect within this bounded region. Therefore, if you pick something from y-axis, you cannot pick anything from the rest of this graph, from any of these hanging bars. From the whole of this side, you cannot pick anything. So if En picks something from here, then it will all be contained in the y-axis. So all of E1 will be there. And then E2 has to contain E1, which means also E2 picks this point from y-axis. And therefore E2 also is completely contained in y-axis. And that will be for every next En. So in this case, the union of En will be just the y-axis. And you will never cover the rest of your set. So that, I think, is sufficient to convince you of this lemma, that you can never write En as a union of increasing sequence of compact connected sets. This increasing, as you saw, also played a big role. And as I said, if you believe in this lemma and you believe in this theorem, it must follow that no matter what metric you put on R2, this particular set that I've drawn a picture of for you will never have finite H1 measure. Looking at this set here, the hanging infinite chimes, it's like this musical instrument chimes. I call this set chimes, or infinite chimes. Obviously has infinite H1 measure. If you look at the Euclidean distance, Hausdorff measure coming with the Euclidean distance. But remember, you can squeeze all of R2 into the unit ball. And in this case, the set E will be transferred somewhere. So infinity is at the boundary. So there will be this point at the boundary, which is not part of your space, which is not part of your set E. And everything else is like the hanging things from there. So these, of course, depends on the particular homeomorphism you find, but these bars and this graph will look something like this, with these vertical bars approaching the y-axis will be transferred into a sequence of such hairs, also converging to a single one. And in this case, it's not obvious that, well, of course, H1 has to be infinite. There's no way, because it has finite diameter, because all of this space has finite diameter too. So again, that's another way of seeing that this H1 equal infinity is not simply an artifact of this E being unbounded in my picture. Even if you draw it inside a copy of R2, a homeomorphic copy of R2 with finite diameter, as I just did, again in that it will have infinite H1 measure. So this set E will have infinite length, no matter how you put a metric on R2 compatible with the topology. And that brings me to the end of this video. And see you in the next one, where we see more fun examples of spaces and their Hausdorff measures and topologies.